Good morning, geometry students. This is Miss Van Horn. I'm gonna try a video to walk you through a lesson and see if this helps you guys a little bit more so I can actually explain as I'm solving through. I'm still gonna send you pictures of the answers and everything like that, but I'm hoping this helps a little bit more because things are getting a little bit more complicated with the material. So what I'm going to do is go through pages 21, 22, and 23 in the packets where we're talking about chords and specifically angles and segments that are created from chords. So you guys should have in your notes that a chord is a segment that connects 2 points on a circle. So just to kind of go over that, if you have a circle with center C, a chord is going to connect 2 endpoints on the circle. So we would say that AB is an example of a chord in circle C. So the goal of this lesson was to describe the relationships between chords and angles in a circle, and I'm going to start off with number 26, where it says, what if it is a semicircle? So it says, what is the measure of an angle when it is inscribed in a semicircle? This is half of a circle or an arc with a measure of 180 degrees. Consider this as you answer the questions below. So for part A, it says, assume that the diagram at right is not drawn to scale. If the measure of arc QR equals 180 degrees, then what is the measure of angle QPR? So they're giving you guys arc, the curve, QR, okay, outside of the circle, and they're telling you this is 180 degrees. Okay. Angle QPR, so from Q to P to R, this angle right here, it's an inscribed angle because the vertex is on the circle and it touches at point P. From yesterday's lesson, you guys should have read through and saw that the inscribed angles are half of the arc measure that they open up to. So notice that angle P opens up to arc QR, or the 180 degrees that we were given. So in order to find the measure of angle QPR, we would take the arc measure and divide it by 2, which is going to give us 90 degrees. Okay, part B, it says, since you have several tools to use with right triangles, the special relationship you found in part A can be useful. For example, UV is a diameter of the circle below. If TU equals 6 and TV equals 8, what is the radius of the circle? And then what is the area? So diameter, which we talked about in the very first lessons of the unit, a diameter goes through the center of the circle and it pretty much cuts it in half. All right, so when looking at segment UV, it's cutting the circle in half. This means that arc UV to the right side of the circle is half of the circle. Well, if there's 360 degrees in a circle, half of that is 180 degrees. Okay. Similarly to part A, you guys have an inscribed angle T, right? So UTV, and that's opening up to the arc of 180. So your inscribed angles are always half of the arc. So if we do again 180 divided by 2, our inscribed angle at T is going to be 90 degrees, which creates a right triangle for us, and we have right triangle tools, such as Pythagorean theorem and trig. Now the word problem also tells us that TU is 6 units long, TV is 8 units long. So I'm going to mark those on the diagram. TU is 6, TV is 8. What we're trying to find is the radius of the circle. Okay, so the radius, remember, is halfway across the circle from the center to a point. Okay, but if we have a right triangle, what we can use is Pythagorean theorem to figure out the diameter. Okay, which again is the distance from U to V all the way across. And if we know the diameter, we can cut that in half to find the radius. So using Pythagorean theorem, let's set up 6 squared plus 8 squared equals d squared. So d is the hypotenuse because it's across from that 90-degree angle. Okay, so longest side of the right triangle. Solving 6 squared, we got 36 and 64. We're going to add these together. That gives us 100. And then square rooting both sides. We would end up with 10 as our diameter. So if we want the radius, what we have to do is take half of the diameter. So 10 divided by 2 gives us 5 for our radius. Okay, so again, looking at your circle, you have 2 radii that make up the diameter. So 5 plus 5 gives you 10, which is the whole thing. This question also asks though for area. So you guys want to use your area formula from lessons last week. And area of all circles is pi r squared. So what we can do is substitute in the radius that we found, and then you guys can give me either an exact answer or an approximate answer, and both would be correct. So we'll do pi 5 squared. If you're doing exact, you're just working with the numbers. You do not type pi in the calculator. So 5 squared is 25, and the pi comes down. If you guys are doing an approximate answer where you type it all in and then you round on your calculator, you can do that as well. So on the calculator, we would do second caret to get your pi, 5 squared, and then we would round this appropriately. So approximate would be 78.54. And we just have units, so we'll do units squared for the area. Okay. So that's walking through number 26. I mean, you guys have a semicircle or a diameter, which is half of the circle. It's creating right triangles for you guys, and that means you guys can use right triangle tools, such as Pythag, to solve for missing parts. Moving on to number 27. It says you have already learned that a chord is a line segment that has its endpoints on a circle. What geometric tools do you have that can help find the length of a chord? So part A, examine the diagram of chord LM and circle P below. So when they have circle P, they're telling you guys that P is the center of the circle. If the length of the radius is 6 units and the measure of arc LM is 150 degrees, find the length of segment LM. So anytime you have information, let's go ahead and mark what we know. So we have the radius is 6 units. However, when I look at our diagram, we don't have any radii drawn in. So maybe we can draw those in. If you guys connect P to L, that's a radius. So we can mark that 6 units long. We can connect P to M, which is another radius, and should also still be 6 units long. The measure of arc LM, so the curve or part of the circumference from point L to point M on the outside, is 150 degrees. Okay, so that's how we would start with the diagram. Right. So notice that at the center of your circle, you guys have angle LPM, right? Angle L. This is a central angle. And from yesterday's lesson, the central angle is the same as the arc that it opens up to. So angle P in the center is also going to be 150 degrees. So now how does that help us? From the previous lesson as well, you guys have notes about how you can draw a radius or diameter that bisects the chord. And when you draw in a radius or diameter that bisects the chord, it cuts it into two equal parts, it does it perpendicularly. So what we do is we create, again, right triangles, and we can use right triangle tools to help us solve for LM. Now what I'm gonna do here, since my diagram is getting a little crammed, I'm gonna take out one of those right triangles and redraw it. So it's a little bit bigger and we understand what's going on. So if I take out my highlighted right triangle, we have L, we have P, we'll label this point O for reference. We have our 90 degrees because it's perpendicular. We have LP is 6. And then similar to area of polygons, if I'm bisecting the chord, I'm also bisecting this central angle. So the central angle gets cut in half. So we do half of 150, which is 75 degrees. So that would be our new angle P in the right triangle. So go back to the directions. We're trying to find the length of LM. How long is it? Okay. So what I'm going to do is place an X on LO. Right? And if we can find the length of X, we know that this would be the same length here. And what we can do is multiply by 2 or add those together to get the whole length. So again, think about what we did with area of regular polygons when we found the base. Once we found that X value, we multiplied it by 2 to get the whole base of the triangle. That's kind of what we're doing here. Using this right triangle now, notice that we want to solve for a side, but we are only given one side and one angle. This is set up for trig. Pythagorean theorem will not help because we don't have this third side. Okay, so what we need to do using our reference angle, let's label our opposite side. Our hypotenuse is always across from the 90. And then our adjacent is going to be the last side. So something you guys know, something you don't, right? The number and the variable, we're using the opposite and the hypotenuse. The trig function that works with opposite and hypotenuse is your sine function, and that's what we're going to use to solve for X. So we will set up sine of our angle 75 degrees, and that's equal to opposite over hypotenuse. So X over 6. So as we've done in class, we can put that over 1 and then do the butterfly, cross multiply to solve for X. 1 times X is X. Sine of 75 times 6. We get multiplied together. Okay. So if you guys have your graphing calculator, if you don't, please go onto your app store through your phone. Android and iPhone both should have a free graphing calculator that you guys can download and use as you guys need to use trig, and this stuff keeps coming up. So I'm gonna hit my mode button real quick. I'm in degree mode, which is good. So I'm gonna go ahead and multiply sine of 75 times 6. And so our X value is going to be 5.80 when we round this. So the 5 is rounding the 9 up to a 10, but a 10 won't fit. 10 rounds the 7 up to an 8. So 5.80 is going to be our answer. Okay, so revisiting the question, the length of LM, if we have X, and this is 580, then over here, OM is 580, and what we want to do is multiply that answer by 2. So LM, our chord, will be 5.80 times 2, which gives us 11.6. We don't have any specific units, so we'll just put units. All right. So that was part A. So again, using right triangle tools. All right, and then towards the bottom, part B. What if you know the length of a chord? How can you reverse the process? Label the circle below with a radius length of 5 units and a chord AB with a length of 6 units. Find the measure of arc AB. So we'll put a center on this circle. We know the circle has a radius of 5, and we want to also put a chord AB in here. So I'm going to try to set it up and model what was in part A. So it kind of looks like that. So I'm going to put point A, a point B, and we'll draw in chord AB. Right, using the given information, it says AB is 6 units long. So I'm just going to put 6. And then drawing in the radii like we did with PL and PM, let's label that C. We'll draw in CA, CB, and they're both radii, so they're both 5 units long. Find the measure of arc AB. So now we're looking for the degrees of this curve. Okay, which as we set up here, the arc measure is the same as the central angle that opens up to that arc. So we want to find this angle. All right, I'm going to go ahead and bisect the triangle. We're going to bisect the chord. And when we bisect the chord, it's creating right triangles because it does it perpendicularly. So similar to the last problem, I'm just going to focus on this right triangle, take it out, make it a little bit bigger so we can see what we're working with. All right, so label this point D. So got A, D, and C. AC is 5. AD, since we bisected the chord, we bisect 6. So half of 6, this would be 3 and 3. So AD is 3 units long. And we're trying to find the angle. So we're going to label the angle theta, since we don't know that. And if you guys remember back from unit 4, this is going to be your inverse trig. So we're still going to label the opposite, the hypotenuse, and the adjacent side and figure out which trig function we're working with. So from theta, your opposite side is 3. Across from 90, this is your hype. And then adjacent has to be your third side, which nothing's there. So similar to part A, we're still working with the opposite and the hypotenuse, which is your sine equation. So we'll still set up an equation using sine, but this time it's going to look slightly different. So we have sine of our angle, which we don't know. It's just theta. Opposite over hypotenuse tells us it's 3 over 5. So if you remember inverse trig, in order to get theta by itself, we have to get rid of the sine function. And we do that by multiplying both sides by inverse of sine. So multiply by sine inverse, right, with that little -1, if you guys remember. And this is going to allow theta to be on its own so we can solve for that angle. Okay. In your calculators or on your app, what you guys are going to do is type in inverse sine of 3 over 5 to get that degree. Okay. So if we go back to our calculators, in order to access inverse sine, that's right above your sine button. It's in blue. So you want to hit your second sine. You guys have the inverse. And then we'll do 3 over 5, or 3 divided by 5 is the same thing. Hit enter, and there we go. So we end up with 36.87 degrees. Right, 36.87 degrees. So that's our angle theta right here inside the triangle. Okay, make sure you go back to the directions. We wanted to find the whole arc measure of AB. That's going to be the same as the whole central angle. So similar to what we did with the x value here, we're going to have to multiply that angle by 2 to figure out the whole central angle, which is the same as the whole arc that we want. Right? So measure of arc AB, we're going to take 36.87 degrees, and we're going to multiply that by 2 and see what we come up with for the final answer. All right. And in my calculator, I'm getting 73.74 degrees. So that would complete page 21. I'm going to go ahead and submit a new video for the next couple pages and run through those real quick. But if you have questions, please take a picture, send it to me, mark it up, let me know what you guys have questions about, and if there's anything I confused you with, walking you through this process, okay? All right, I'm going to go ahead and make the next video.